So for this chapter we have a number of outlines and a number of objectives that should be achieved. First of all, the outlines are a basic concepts regarding operating system structures and components, scheduling criteria, scheduling algorithms, thread scheduling, multiple processor scheduling, operating system examples, and at the end a number of criteria or a number of methods to evaluate algorithms. At the end of this chapter we should achieve the following objectives: introduce CPU scheduling, which is the basis for multiple programming operating systems; to describe various CPU scheduling algorithms; to discuss at the end evaluation criteria for selecting a CPU scheduling algorithm for a particular system. As an introduction, we can say that almost all programs have some cycle of CPU number crunching and waiting for input output of some kind. Even a simple fetch from memories take actually a long time relative to CPU speeds. In simple systems running a single processor, actually the time spent waiting for input output is wasted, and thus CPU cycles are lost forever. A scheduling system allows one process to use the CPU while another is waiting for input output, thereby making full use of otherwise lost CPU cycle. The challenge here is to make the overall system as efficient and fair as possible. Actually today we will say what do we mean by efficient and fair as possible as we can, and these points are subject to varying and often dynamic conditions, and where efficient and fair are somewhat subjective terms, often subject to shifting priority policies. Almost all processes alternate between two states in a continuing cycle, as shown in this figure. Actually, it alternates between a CPU burst, which is performing some calculations, and an input-output burst waiting for data transfer in or out of the system. CPU bursts vary from one process into another and from one program into another, but an extensive study shows a frequency pattern similar to that shown on the next figure, which I will show you in 1 minute. So what do we mean by that is, first, CPU input burst cycle, a process will run for a while. It is called a CPU burst. Perform some input output actions, it is called an input output burst. Then run for a while more, the next CPU burst. How long between input output operations depends on the process. Processes that perform lots of input-output operations are called input-output bound processes. Each input-output operation is followed by a short CPU burst to process the input-output. Then more input-output happens. CPU-bound processes are processes that perform a lot of computations and do a little of input-output. Actually, when look at CPU burst time across the whole system, it has an exponential distribution, as the figure in front of you. What are the possible process states? Actually, the processes moves from running state, which is the process is running on the CPU, to a ready state, ready to run but not actually running on the CPU. And the third most important state is the waiting state, which indicate that the CPU is waiting for some event like input output to happen. When do scheduling decisions take place? When does CPU choose which process to run? There are a variety of possibilities. When a process switches from running to waiting, could be because of input-output request, or because waiting for a child to terminate, or waiting for synchronization operations, which actually we will speak in details in chapter number 6, CPU synchronizations. Also, a process switches from running into a ready in completion of interrupt handler. For example, a common example of interrupt handler, the time interrupt in an interactive system. If the scheduler switches processes, in this case it has pre-emitted the running process. Another common case interrupt handler is the input-output completion handlers. Also, it may happen that we need to switch from one process into another when we switch from a waiting state into a ready state. And actually an example of this case, when the state or when the process do a complete or has completed its request for input output resource, and at the end when a process terminates. Actually, for conditions 1 and 4, there is no choice. A new process must be selected. So when we say we need to switch from running to waiting, or we need to say that we need to switch a process from running to waiting, or we have a case that a process has terminated, the scheduler should select a new process from the ready queue. For conditions 2 and 3, switching from running to ready state and switching from waiting to ready state, there is a choice. Either to continue running the current process or to select a different one. If scheduling takes place only under conditions 1 and 4, the system is said to be non-preemptive or cooperative. Under these conditions, once a process starts running, it keeps running until it blocks itself or it finishes, terminates. Otherwise, the system is said to be preemptive. For an example, Windows actually used non-preemptive scheduling up to Windows 3.x and started using preemptive scheduling with Windows 95. Macs used non-preemptive prior to operating system X and preemptive since then. Note that preemptive scheduling is only possible on hardware that supports a timer interrupt. Dispatcher. The dispatcher actually is the module that gives control of the CPU to the process selected by the scheduler. This function involves switching contacts, switching to user mode, we mean switching from kernel mode into a user mode, then jumping to the memory location of the program to restart that program. We mean that jumping to the proper location in the newly loaded program in the memory, in the RAMs. The dispatcher needs to be as fast as possible as it runs on every context switch. The time consumed by the dispatcher, which is lost, this time the CPU is ideal, and actually that's why we say the time is lost. It is called a dispatch latency, which is the moving or the stopping of one process and the starting of another process. We should try to make this time as short as possible. Scheduling criteria. Actually, there are several different criteria to consider when trying to select the best scheduling algorithm for a particular situations and environment, including CPU utilizations, which is ideally the CPU would be busy 100% of the time, so as to waste 0 CPU cycles on a real system. CPU usage should range from 40% to 90%. We mean by utilization is to keep the CPU as busy as possible. Actually, we can do that by increasing multi-programming. What do we mean by multi-programming? Multi-programming means that more than one process, which ideally a job, more than one job are residing inside the main memory, the RAMs, at the same time. The second criteria is called the throughput, which measures the number of processes that complete their execution per unit of time. It should range from 10 per second to 1 per hour, depending on the specific processes. The third criteria is called turnaround time, which actually we will see while evaluating CPU scheduling algorithms. It is the amount of time took to execute a particular process from submission time to completion. The third criteria is called the waiting time. How much time processes spend in the ready queue waiting their turn to get on the CPU is called the waiting time. Response time, it is the time taken in an interactive program from the issuance of a command to the comments of a response to that command. In general, one wants to optimize the average value of a criteria, so we should maximize the CPU utilizations, we should maximize the throughput, and also we should minimize all the others, the turnaround time, the waiting time, and the response time. However, sometimes one wants to do something different, such as to minimize the maximum response time. Sometimes it is most logical to minimize the variance of a criteria than the actual value. Users are more accepting of a consistent, predictable system than an inconsistent one, even if it is a little bit slower. Now we are going to discuss some scheduling algorithms. Actually, we have a number of subsections which we will explain several common scheduling strategies looking at only a single CPU burst each for a small number of processes. Real systems have to deal with a lot more simultaneous process executing their CPU input-output burst cycles. First of all, the first scheduling algorithm is called first come first serve. It is like the concept of data structure queue, which is first in first out. First come first serve is very simple, just it is like a FIFO queue, like customers waiting in line at the bank or the post office or at a copying machine. Unfortunately, however, first come first serve can yield some very long average waiting times, particularly if the first process to get there takes a long of time. For example, consists the following three processes. Actually, I have three processes at the three processes in the ready queue at time equals 0. We have a process number 1 which needs 24 millis of seconds of the time of the CPU. I have a process number 2 which needs 3 milliseconds, and the process number 3 which needs also 3 milliseconds. In the first Gantt chart in front of you, process 1 arrives first. The average waiting time for the three processes is 0 for process number 1, 24 milliseconds for process number 2, and 27 milliseconds for process number 3. So the average waiting time for the three processes is 0 plus 27 plus 24 over 3, which is 17 milliseconds, which is actually a long average waiting time. In the second Gantt chart below, the same three processes have an average waiting time of 0 plus 3 plus 6 over 3, which is 3 milliseconds. The total runtime for the three bursts is the same, but in the second case, 2 of the 3 finishes much quicker and the other process is only delayed by a short amount. First come first serve can also block the system in a busy dynamic systems in another way, known as convoy effect. When one CPU intensive process blocks the CPU, a number of input-output intensive processes can get backed up behind it, leaving the input-output devices ideal. So, actually, first come first serve scheduling algorithm is simple. Its average waiting time differs regarding the CPU burst time for each process, and you have seen that for same three processes, when we change the order of the processes, actually the average waiting time falls in a dramatic way. Second algorithm that we are going to discuss today is the shortest job first. It is called SJF scheduling. The idea behind the shortest job first algorithm is to pick the quickest, fastest little job that needs to be done, get it out of the way first, and then pick the next smallest, fastest job to do next. Technically, this algorithm picks a process based on the next shortest CPU burst, not the overall process time. For example, of shortest job first, the Gantt chart in front of you is based upon the following CPU burst times and the assumption that all the jobs arrive at the same time. Actually, I have process number 1 that needs 6 milliseconds, process number 2 needs 8 milliseconds, process number 3 needs 7 milliseconds, and process number 4 needs 3 milliseconds. In the case above, the average waiting time is 0 plus 3 plus 9 plus 16 over 4, which is about 7 milliseconds. Actually, if we try to do this example on first come first serve, actually it will needs about 10.25 milliseconds to complete. So SGF can be proven to be the fastest scheduling algorithm, but it suffers from one important problem. How do you know how long the next CPU burst is going to be? Actually, it is the most difficult issue regarding shortest job first. So, how do we know how long the next CPU burst is going to be? For long-term batch jobs, this can be done based upon the limits that users set for these jobs. But this issue doesn't work for short-term CPU scheduling as on interactive systems. A more practical approach is to predict the length of the next burst based on some historical measurements of the recent burst times for this process. One simple, fast, and relative accurate method is the exponential average, which can be defined as follows. The estimated time for I plus 1 is equal to alpha multiplied by the burst time of I, which is the previous process, plus 1.0 minus alpha, all multiplied by the estimated time of I. This means that the previous estimate contains the history of all previous times, and the alpha serves as a weighting factor for the relative importance of recent data. Vice versa, past history. If alpha is 1, then the past history is ignored, and we assume that the next burst will be the same length as the last burst. If alpha is equal to 0, then all the measured burst time are ignored, and we just assume a constant burst time. Most commonly, alpha is set at 0.5. Shortest job first can be either pre-emittive or non-pre-emittive. Pre-emission occurs when a new process arrives in the ready queue that has a predicted burst time shorter than the time remaining in the process whose burst time is currently on the CPU. Pre-emittive shortest job first is sometimes referred as shortest remaining time first scheduling. So, as I have said, shortest job first can be either pre-emittive or non-pre-emittive. A pre-emittive version of shortest job first occurs when a new process arrives in the ready queue that has a predicted burst time shortest than the remaining time in the process whose burst is currently on the CPU. Pre-emittive shortest job first is sometimes called shortest remaining job first. For example, let's assume that we have 4 processes, and actually the arrival time differs. Process 1 arrives at time 0, process 2 arrives at time 1, process 3 arrives at time 2, process 4 arrives at time 3. This means that actually we should check after a period of time. We should check the ready queue. We should check the processes inside the ready queue and check their burst time. If we have a process that has a burst time less than the process running, we should pre-emit this process, change it into a waiting one, and start the another one. Actually, at arrival time 0, process 1 will begins, but at time equal 1, actually I have in the ready queue 2 processes, process number 1 and the process number 2. Process number 1 needs 8 minus 1, which is 7 milliseconds, and the process number 2 needs 4 milliseconds. If we apply shortest remaining job first, this means that process 1 should be switched from running to waiting, and we should choose process number 2. Actually, process number 2 will start working at arrival time 2. Process 3 enters the ready queue. If we check the ready queue, we will have 3 processes. Process number 1, which needs 7 milliseconds of the time of the CPU. Process number 2, which needs actually 4 minus 1, which is 3 milliseconds, and the process number 3 needs 9 milliseconds. The shortest one among the 3 processes is the process number 2, and so on. If we calculate the average waiting time for the 4 processes, we will get the average waiting time for process number 1 is 10 minus 1, which is equal to 9. The average waiting time for process number 2 is 0, because actually process number 2 arrives at time equal 1 and start executing at time equal 1 also. So the waiting time for process number 2 is 0. The waiting time for process number 3 is 15, because the process number 2 arrives at time equal 2 and start executing at time equal 17. 17 minus 2 is equal to 15. And the waiting time for process number 4 is 5 minus 3, which is equal to 2. So the average waiting time is 0 plus 9 plus 2 plus 17 over 4, which is about 6.5 milliseconds, as opposed to 7.75 milliseconds for non-pre-emittive shortest job first, and about 8.75 milliseconds for first come first served scheduling algorithm. Assume that we have the following processes, and I asked you to find out the finish time, the waiting time, and the turnaround time of each process for the following scheduling algorithms: first come first served, shortest job first, and the shortest remaining job first. Actually, I have 4 processes: process A, process B, process C, process D. The burst time is 30, 20, 12 and 10, and the arrival time is 0, 5, 10 and 15. For first come first serve, processes will run in the order they arrive. The following is the finish, the turnaround, wait, and the waiting time for each process. And the average waiting time will be 0 plus 25 plus 40 plus 47 over. If you try the same example on the shortest job first, actually process number 1 will start, because our time equals 0, we have only process number 1, which is the process A. It will work for 30 milliseconds. After that, we have 3 processes on the ready queue, B, C and D. The shortest one among them is D, so D will work for 10 milliseconds. After that, we have 2 remaining processes, process B and process C. Process C has the shortest burst time, so process C will work for 12 milliseconds, and at the end process B will work for 20 milliseconds. The average waiting time will be 0 for process number A or process A, 15 for process B, 30 for process C and 47 for process D. The average waiting time will be 0 plus 15 plus 30 plus 47 over 4. I advise you to do all these examples at home so that you will gain an experience on drawing a Gantt chart, calculating the waiting time for each process, then calculating the average waiting time for the whole system. If we try the same example for the shortest remaining job first, actually here we should pay attention to the arrival time. Process A will work for 5 milliseconds, then process B will work for 5 milliseconds, process C will work for 12 milliseconds, process D will work for 10 milliseconds, then we return the turn to process number B for 15 milliseconds, and at the end process number A, which is the last remaining process, for 25 milliseconds. The average waiting time will be 42 for the process A, 22 for process B, 0 for process C, and 7 for process D. Actually, from the below example, we can conclude that shortest remaining job first is a very good example for the processes which needs a short time among long times. Actually, if we work on shortest job first, we will have a problem of starvations for short CPU burst time processes. Next scheduling algorithm is called the priority algorithm. The priority algorithm is a more general case of shortest job first, in which each job is assigned a priority, and the job with the highest priority gets scheduler first. We mean the shortest job first uses the inverse of the next expected burst time as its priority. The smaller the expected burst, the higher the priority. Note that in practice, priorities are implemented using integers within a fixed range, but there is no agreed upon convention as to higher priorities use large numbers or small numbers. In this book, low numbers are used for high priorities. This means that 0 will be the highest possible priority. Priorities can be assigned either internally or externally. Internally, priorities are assigned by the operating system using criteria like average burst time, ratio of the CPU, or system resources used, and other factors available to the kernel. External priorities are assigned by the users based on the importance of the job for the user. Priority scheduling can be either a preemptive or non-preemptive, but the most important aspect is that priority scheduling can suffer from a major problem known as indefinite blocking or starvations, in which a low priority task can wait forever because there are always some other jobs around that have higher priority. The solution to this problem is called aging solution, in which priorities of jobs increases the longer they wait. Under this scheme, a low priority job will get its priority raised high enough that it gets run. For an example, if I have 5 processes, and actually for each process I have the CPU, burst time, and the priority. For the example in front of you, process B will start executing because it has priority equal to 1, which means that it is the highest priority. So process 1 will work for 1 milliseconds. After finishing, we check the ready queue. In the ready queue we have a process A, C, D, and E, but the next one to be executed will be process E because it has the next highest priority, so it will work for 5 milliseconds, from 1 millisecond till 6. Then we have process A, which has the next highest priority. It will work from 6 till 16 for 10 milliseconds. After A, process C will work from 16 till 18, and at the end process D will work for 1 millisecond. From the example, we see that process D is serving from starvations, or I mean it is suffering from starvations because actually it needs a long time of burst time, but it should wait for the highest priority processes to finish working before having its time to do its work. So what we did in this example, we did the priority scheduling using non-preemptive technique. What I suggest you to do is to try this example at home using preemptive priority scheduling, which is the same as the previous scheduling algorithms. The last, or actually it is not the last scheduling algorithm. Now we will speak about round robin. RR scheduling algorithm, which is similar to first come first serve scheduling, except that CPU bursts are assigned with limits called a time quantum. When a process is given the CPU, a timer is set for whatever value has been set for a time quantum. If a process or if the process finishes its burst time before the time quantum timer expires, then it is swapped out of the CPU, just like the normal first come first served algorithm. If the timer goes off first, then the process is swapped out of the CPU and moved to the back end of the ready queue. The ready queue is maintained as a circular queue, so when all the processes have had a turn, then the scheduler gives the first process another turn, and so on. RR scheduling can give the effect of all processors sharing the CPU equally, although the average waiting time can be longer than with other scheduling algorithms. Let's take the following example. In the following example, we have three processes: process 1, process 2, process 3. Actually, this is the example which we tried first for first come first served. We have a process 1 that needs burst time 24, process 2 3, and process 3 3 milliseconds also. Let's assume that the time quantum is equal to 4. This means that the first process will work for 4 milliseconds, and after that it will be swapped out the end or the back end of the ready queue. Then process 2 will work for only 3 milliseconds, even that the quantum time is equal to 4 milliseconds, but the burst time of process 2 is less than the quantum time, so the process 2 will be swapped out of the CPU, I mean. Then process 3 will work for 3 milliseconds and will be also swapped out of the CPU. Then process we will give the turn back to process number 1, which will works for about 1, 2, 3, 4, 5 time quantums to finish its burst time, which is 24 milliseconds. Typically it has a higher average turnaround time than shortest job first, but it has a better response time. The performance of round robin is sensitive to the time quantum selected. If the time quantum is large enough, then round robin reduces to the first come first served algorithm. If it is very small, then each process gets about 1 over n of the processor time and shares the CPU equally. But a real system involves overhead for every context switch, and the smaller the time quantum, the more context switches there are. Most modern systems use time quantum between 10 and 100 milliseconds, and the context switch times on the order of 10 microseconds. So the overhead is small relative to the time quantum. Turnaround time also varies with the quantum time in a non-apparent manner. For example, if we consider the following example, as I have said in the previous slide, actually The performance of round robin is sensitive to the time quantum selected, and whenever we have a time quantum which is large enough, this means that I am reducing the number of the context switches, and whenever I have a smaller time quantum, I will have more context switch. Turnaround time is also, or turnaround time also varies with the time quantum. Let's consider the following processes shown in this figure. Actually, I have a process number 1 which needs a burst time 6, process number 2 that needs a burst time 3, process number 3 needs 1, and the process number 4 needs 7. And we see that turnaround time is minimized if most processes finish their next CPU burst time within one time quantum. For example, with 3 processes of 10 milliseconds bursts each, the average turnaround time will be about 1 millisecond quantum is 29, and for 10 millisecond quantum it reduces to 20. However, if it is made too large, then round robin just degenerates to first come first served. As a rule, 80% of the CPU bursts should be smaller than the time quantum. The next algorithm is called the multi-level queue algorithm. When we have processes that can be categorized, then multiple separate queues can be established, each implementing whatever scheduling algorithm is most appropriate for that type of a job. Scheduling must also be done between queues, that is, scheduling one queue to get time relative to other queues. Two common options are strict priority, no job in a lower priority queue run until all the higher priority queues are empty, and round robin, where each queue gets a time slice in turn, possibly of different sizes. Note that under this algorithm, jobs cannot switch from one queue into another. Once a process are assigned a queue, that is its queue until it finishes its work. This is an example of a multi-level queue scheduling in which system processes, interactive processes, and interactive editing processes are given the highest priority among batch processes and, for example, student processes. The next algorithm that we are going to discuss is the multi-level feedback queue scheduling. Actually, the multi-level feedback queue scheduling is like the multi-level queue scheduling. Multi-level feedback queue scheduling is similar to the ordinary multi-level queue scheduling described above, except jobs may be moved from one queue to another for a variety of reasons. If the characteristics of a job change between CPU intensive and input output intensive, then it may be appropriate to switch a job from one queue into another. Aging can also be incorporated so that a job that has waited for a longer time can get pumped up into a higher priority queue for a while. Multi-level feedback queue scheduling is the most flexible scheduling algorithm because it can be tuned for any situations, but it is also the most complex to implement because of all the parameters. Some of the parameters which define one of these systems include the number of queues, the scheduling algorithm for each queue, the method used to upgrade or demote processes from one queue into another, which may be different, the method used to determine which queue a process enters initially is also a parameter that affects the definition of the multi-level feedback queue scheduler. As an example, let's take 3 queues. On the first queue, round robin with time quantum 8 milliseconds will work. On the second queue, round robin with time quantum 16 milliseconds will work, and for the last queue, first come first serve algorithm will work. A new job enters queue 0, which is served for round robin and for time quantum equal 8. When it gains CPU, the job receives 8 milliseconds. If it doesn't finish in 8 milliseconds, the job is moved to queue 1. At Q1, the job is again served round robin and receives about 16 additional milliseconds. If it is still doesn't complete, it is pre-emitted and moved to queue number 3, and so on. The following figure shows how a process moves from one queue into another. If it finishes its work in one queue, it will be swapped out, otherwise it will be moved to the next queue and the next queue till finishing. Actually, what we did in the previous slides, we talk about scheduling of processes. The process scheduler schedules only the kernel threads, while the user threads are mapped to the kernel threads by the thread library. The operating system is unaware of them. So, there is a distinction between the user level threads and the kernel level threads. Contention scope refers to the scope in which threads compete for the use of the physical CPUs. On systems implementing many-to-one and many-to-many threads, process contention scope PCS occurs between threads that are a part of the same process. This is the management scheduling of multiple user threads on a single kernel thread, and it is managed by a thread library. System contention scope SCS involves the system scheduler scheduling kernel threads to run on one or more CPUs. System implementing one-to-one threads like XP, Solaris 9, Linux use only system contention scope. Process contention scope scheduling is typically done with priority, where the programmer can set or change the priority of the threads created by his or her program. Even time slicing is not guaranteed among threads of equal priority. If we need to speak about thread scheduling, let's start with pthread library, which works on a process contention scope and system contention scope. Actually, the pthread library provides for specifying scope contention, pthread scope process, which schedulers threads using process contention scope by scheduling user threads into available lightweighted process using the many-to-many model. And it has a pthread scope system that schedulers threads using system contention scope by binding user threads to a particular lightweighted process implementing one-to-one model. Get scope and set scope methods provide for determining and setting the scope contentions. As we see on the code in front of you, actually I have a method called set, which I use in order to set the scheduling algorithm to the process or to system, to process contention scope or system contention scope regarding the threads I am working on. Actually, we should have a general idea about pthread scheduling API, and there is no need to go in details regarding the code. Multi-processor scheduling. When multiple processors are available, then scheduling gets more complicated, because now there is more than one CPU which must be kept busy and in effective use all the times. There is a number of factors that we should pay attention while dealing with multi-processor scheduling. Load sharing revolve around balancing the load between multiple processors. Multiprocessor systems may be heterogeneous systems, which means different kinds of CPUs, or homogeneous, which mean all the same kind of CPU. Even in the later case, there may be special scheduling constraints, such as devices which are connected via a private bus to only one of the CPUs. For this book, we will strict in discussion of homogeneous systems, and we will not speak about heterogeneous systems. First point we will discuss is about symmetric and asymmetric multiprocessing. Actually, asymmetric multiprocessing is when one process among the number of processes is the master, controlling all the activities and running all the kernel code, while the other runs only user code. This approach is simple, as there is no need to share critical system data. The another approach is called symmetric multiprocessing, SMP. where each process schedules its own job, either from a common ready queue or from separate ready queue for each processors. Virtually all modern operating systems support symmetric multiprocessing, including XP, Windows 2000, Solaris, Linux, and Mac operating systems. The second approach or factor that we should pay attention is the processor affinity. Processors contain cache memory which speeds up repeated accesses to the same memory locations. If a process were to switch from one process to another each time it got a time slice, and the data in the cache would have to be invalidated and reloaded from main memory, thereby we will not be benefiting from the cache. Therefore, symmetric multiprocessing systems attempt to keep processes on the same processor via processor affinity. It is called the soft affinity. When the system attempts to keep processes on the same processor but there is no guarantee. Linux and some other operating systems support another type of affinity. It is called the hard affinity, in which a process specifies that it is not to be moved between processors. Main memory architecture can also affect process affinity. In particular, CPUs have faster it has a faster access to the memory on the same chip or board than to another memory located elsewhere. If we have a look to this figure, actually if a process has an affinity for a particular CPU, then it should be assigned memory storage in local fast access areas. Multi-core processors in traditional symmetric multiprocessor require multiple CPU chips to run multiple kernel threads. Recent trends are to put multiple CPUs, cores, onto a single chip, which appear to the system as a multiple processors. Compute cycles can be blocked by the time needed to access the memory, whenever the needed data is not already present in the cache. So if we have a look to the to this figure, we have as much as half of the CPU cycles are lost to memory stall. By assigning multiple kernel threads to a single processor, memory stall can be avoided or can be reduced by running one thread on the processor while the other thread waits for the memory. What we did in the previous slides, actually we talk about a system with multiple CPUs which are ready for execution, and we talk about scheduling algorithms which determines which process should run first. As a conclusion, the first step in determining which algorithm and what parameter setting within that algorithm is optimal for a particular operating environment, is to determine what the criteria are to be used, what goals are to be achieved, and what constraints, if there is any constraints, must be applied. For example, let's say one might want to maximize CPU utilizations, which is subject to a maximum response time of 1 second, for example. Once a criteria has been established, then different algorithms can be analyzed and a best choice will be determined. So on the next coming slides, we will talk about different methods for determining the best choices, which is what we are going to do is the methods used to evaluate scheduling algorithm. The first method is called the deterministic modeling. The deterministic modeling, let's say if we have a specific workload is known, then the exact values for the major criteria can be fairly and easily calculated, and the best determined. For example, let's consider the following workload. If I have 5 processes, process number 1 needs 10 milliseconds, process number 2 needs 29 milliseconds, process number 3 needs 3 milliseconds, process number 4 needs 7 milliseconds, and the process number 5 needs 12 milliseconds, with all the processes arriving at time 0. Then the resulting schedules determined by 3 different algorithms will be respectively the average waiting time for first come first serve will be 28, for shortest job first will be 13 milliseconds, and for round robin will be 23 milliseconds. Deterministic modeling is fast and easy, but it requires a specific known input, and the results only apply for that particular set of input. However, by examining multiple similar cases, certain trends can be observed, like the fact that for processes arriving at the same time, shortest job first will always yield the shortest average waiting time, for example. Second evaluation criteria is queuing models. We mean by queuing models is that specific process data is often not available, especially for future times. However, a study of the historical performance can often produce statistical descriptions of certain important parameters, such as, let's say, the rate at which new processes arrive, another information like the ratio of CPU burst to input-output times, or the distribution of CPU burst time and input-output burst time, etc. Armed with those probability distribution and some mathematical formula, it is possible to calculate certain performance characteristics of individual waiting queue. It is called Little's formula, that says for an average queue length of n with an average waiting time in the queue of W and an average arrival of new jobs in the queue of lambda, then these 3 terms can be related by n is equal to lambda multiplied by W. Third evaluation criteria is called simulations. which is to run computer simulations of different proposed algorithms under different load conditions and to analyze the results to determine the best choice of operation for a particular load pattern. The last criteria, which is the only real way, is to determine how a proposed scheduling algorithm is going to operate is by implementing it on a real system and then evaluating the results provided by the implementation. As a conclusion, what we have seen today is an important aspect of multi-programming environment in which multiple CPUs are residing in the main memory, the RAMs, at the same time. So we have multiple CPUs residing on the ready queue. The most important questions arise here is which process should be selected first. This important questions is equivalent to the work done by the important components of the kernel called scheduler and dispatcher. That's why we have seen a number of scheduling algorithms that determines which process to be selected next with respect to a number of parameters and criteria. And at the end of this chapter we have done or we see a number of criteria to evaluate an algorithm. On the next session, on next week, we will go in details about CPU synchronizations or process synchronizations, especially in multi-processor environments. Till that time, I advise you to have a look to the book, chapter number 5. Try doing some exercises regarding CPU scheduling algorithms, especially first come first serve, shortest job first, shortest remaining job first, and round robin algorithm. And I should not forget a priority scheduling algorithm also. Actually, I think that we will have a question regarding the scheduling algorithms on the final. So I will prepare a number of questions and their answers, and I will try uploading them to the Moodle, so all of you will have access to such informations. I wish you a happy time, and don't hesitate to ask me or to send me any inquiry via Moodle regarding the chapter number 5, process scheduling. See you next time, guys. Thank you.